My name is Cody Hergenrother, and I will be doing this presentation on the paper titled Why Fly? Detecting Privacy Invasion Attacks by Consumer Drones. First, some acknowledgments. The authors of this paper, Simon Birnbach, Richard Baker, and Ivan Martinovic, were all from the University of Oxford. This paper was first presented at the NDSS in 2017 between February 26th and March 1st. For anybody interested, I have put links to the paper and this presentation at the bottom. Drones have become much more commonplace in our daily lives. At the time of writing in 2017, there were 1.9 million drones sold in the hobbyist market alone. They're no longer limited to just militaries and enterprise businesses. They've become much cheaper to buy and easier to fly, bringing them into the realm of consumers and hobbyists. Most drones come with high-quality video cameras, making it easy to connect them with a phone or a tablet, anything using Wi-Fi to control the drone and stream live video. Due to the increased prevalence of these drones, there's an inherent increase in risks to privacy invasions by consumer drones and their operators, spying on individuals in areas that without drones would be private and inaccessible. This paper focuses on privacy invasion through windows in people's homes. While there are existing drone detection systems, many are aimed at large businesses and their security forces and law enforcement, not the everyday citizen. Some of the existing detection system methods include radar, video and image analysis, acoustic via microphone arrays, and hybrids of all of these. Many of them are too expensive for the everyday user. Most are too hard to deploy, and some, like radar and video and image analysis, are not specific enough in that either they are too close in size or motion to birds, or that there are too many different drone shapes, as in the method of trying to detect based on appearance alone. The problem that the authors set out to solve in this paper is that existing drone detection systems are expensive and difficult to deploy, or they are insufficient for exclusively detecting drones. They were not designed with the average individual in mind. The author's goal in this paper was to create a drone detection system that is affordable, accessible, and effective, specifying the use of inexpensive, commercial, off-the-shelf hardware that requires minimal prior configuration to set up. The system should have the ability to detect a drone that is performing an invasion of privacy. It should be robust in that it is effective against many different types of drones, and not just one manufacturer or type. For the adversary model, some assumptions are as follows. The adversary's objective is to capture video of the inside of a neighbor's home that is normally inaccessible or visible without a drone. The author assumes that the adversary is using an unmodified, commercially available drone, and that they do not have the ability to modify it. They do not have access to the property and are some distance away from the window. The adversary must get the drone within line of sight of the window, close enough to see inside via the camera. The adversary cannot fly the drone too close to the building, as it's difficult to control flight and increases the risk of detection or interception. The drone's approach speed is only limited by its capabilities. The drone is streaming via Wi-Fi. Line of sight to the receiver causes direct path to be the major contributing factor, so we can ignore multipath effects, absorption, and other effects. The free space path loss is the only cause considered for signal attenuation. Here we have a base case for our system model. We have the target window here and the Wi-Fi receiver attached to it. This angle gamma is for both the field of view for the drone looking to get footage inside of the window, as well as for line of sight from the Wi-Fi receiver. The drone will start here at our launch distance and accelerate upwards. From there, it will then travel from distance L to distance S, where it will begin surveillance and try to remain as still as possible. Once surveillance is complete, the drone will return to its launch point and land. Here we see an overview of the detection process. First, we have pre-processing, where we filter the individual data flows coming in. Then we perform statistical tests to determine if they are drones. If they are drones, we then perform the attack analysis and determine in what attack phase we are in, and if appropriate, whether or not the drone has actually reached the surveillance distance. Now we'll take a look at the pre-processing phase in the detection process. The receiver is likely seeing numerous data flows, so we want to separate those based on MAC addresses. We're assuming the 802.11 Wi-Fi standard. Then we want to ignore the flows that are not exhibiting continuous high bandwidth usage, as this is characteristic of our assumption that the drone is transmitting a continuous live video stream. Now we'll look at the statistical portion of the detection process. One of our assumptions is that the drone is operating in free space and needs to establish line of sight. Therefore, the received signal strength is dominated by the direct path component and the multipath effects can be ignored. The changes in the signal intensity at the receiver are attributed to free space path loss, which is the attenuation of a signal as it travels through the air and is proportional to the square of the distance. So, we expect to see the signal intensity increase as we approach the window, remain stable during surveillance, and decrease during the escape. Now we look at the basis of detection. The received signal strength of the drone's wireless communication is the main component that is used for detection. Specifically, we look at the standard deviation of a sample of packets within a time window. The standard deviation of the signal is averaged over two types of rolling windows. The signal strength variance of packets from a known static transmitter is monitored. The authors recommend and use in their experiment a Wi-Fi access point. The standard deviation of the signal strength from the access point gives a baseline for the noise component that the receiver will see. Due to the high packet rate coming from the drone as it's recording video, we expect to see that over a very short time period, the drone's movement does not affect the signal strength enough for it to be distinguishable from noise. Authors expect that the standard deviation of the signal strength within this short period of time to be near that of the general noise level. Over a long time period, the drone's movement is the major component that affects the signal strength, and we expect to see that the standard deviation will be larger than the noise over a long period of time if the drone is moving. By comparing both the short and long-term standard deviations of the received signal strength, we can draw some conclusions about the transmitter. A low short-term standard deviation, along with a high long-term standard deviation, implies that we have a line-of-sight transmitter that is moving in free space, such as a drone. A high short-term standard deviation, along with a high long-term standard deviation, indicates that we have a transmitter that is moving without line of sight, such as a transmitter that is indoors or moving around on the ground. We are now faced with the question of how to determine the size and time of the short and long-term windows over which we will sample the received signal strength and calculate a standard deviation. In order to determine an appropriate threshold for free space propagation, which is in the short time window, we first calculate the free space path length for each transmission within a time window. We then calculate the standard deviation of samples within that window. We repeat this until we find the maximum window size where the standard deviation within the small time window is below the noise threshold. We then determine the variance of the signal strength, which is the free space path length, and the noise to determine the threshold for free space propagation. In order to conservatively calculate the free space path loss for the short time window, we use the fastest speed that the drone could be traveling. This will allow us to have a high certainty that the speed of the drone will not affect the test of it being in free space, which should be irrelevant of speed. This fastest speed will be as it approaches the surveillance distance. So now we have a short time window, WS, that we want to take samples in. And as the drone is flying, each packet is sent, and each one will experience a different free space path loss as the distance changes. We will perform that free space path loss calculation for numerous small window sizes until we find the largest window size where the standard deviation remains under that noise threshold that we found. And that will give us the small window. Variance in the signal strength is the free space path loss and the noise summed together. They are both independent variables, so there's no covariance. With the equation below, when you work it out, it eventually simplifies down to this value here, which we use as our threshold for the short time window. The steps in determining the threshold for movement, which is the long time window, is the same as for the short time window, with the only difference being that instead of calculating the maximum window size, we will now be looking at the minimum window size where the standard deviation is above the noise threshold. In order to conservatively calculate the free space path loss for the long time window, we use the slowest speed that the drone could be traveling. This will allow us to be confident that at whatever speed, even its slowest, we will still be able to detect the movement. This slowest speed will be as it moves away from the launch distance. So now we have a long time window, WL, during which the drone is flying, and as it sends its packets, they will experience a different free space path loss as the distance changes. Notice that now, instead of adding this term to the distance, we are subtracting it as we are departing from the launch distance. As in the slide for the shortest time window, we were approaching ds. Again, as in the calculation for the small time window, we're going to perform the free space path loss calculation for numerous large window samples, changing the window size until we find this time the smallest window size where the standard deviation is greater than the noise threshold that is found, and that will give us the large window. Calculating the variance of the signal strength, it's the same as for the small time window. The only difference now is that our sign here is different. The threshold itself is still the same. So again, in summary, when the standard deviation of the received signal strength for a sample set within the small window is less than our threshold, we have free space propagation. When the standard deviation of the received signal strength for a sample within the long window is greater than our threshold, we have movement. So we have now covered the pre-processing and statistical test phase, and will now move on to the attack analysis phase. Analyzing the attack phase, we take the difference of the first and second halves of the received signal strength in the long time window. If it is greater than 0, the drone is approaching. If it is less than 0, it is escaping. However, if it equals 0, this does not necessarily indicate that surveillance is occurring, as it could be outside the field of view of the window or some distance off. In order to determine whether no change in the signal strength is actually indicative of a drone surveillance happening, a proximity test is used in conjunction with the attack phase determination. If an approach has already been detected, then a threshold needs to be determined that would indicate the drone has gotten close enough for surveillance to occur. The long window when the approach was detected is used, along with the speed at which the drone was traveling. As before, we take the standard deviation of the measurements over the long window, and we get the threshold sigma p. If the change in the signal strength is greater than or equal to this proximity threshold, then the drone is at the surveillance distance. Here we see a simulation for the attack phase analysis. The long window standard deviation breaches the threshold at the approach phase and the escape phase, while during the surveillance phase it remains below our threshold here. During the short window standard deviation, it stays below the threshold the whole time. For the attack phase, the proximity threshold is shown here. So as the change in our signal strength increases, it indicates we're getting closer to the receiver. Until we cross this threshold, that's when we know that we've reached the surveillance distance. From there, the drone stops, slows down, and begins surveillance before escaping. The time it takes the system to detect an attacker is equal to the long window time, and the range is equal to the launch distance minus the long window time multiplied by the speed of the drone. Since the actual speed of the drone is not known beforehand, multiple long window times are computed in parallel to guarantee a timely detection. Here we see a depiction of the detection algorithm looking at the data flow for one transmitter. We use increasing values of the long window and compare the short window standard deviation with our threshold to determine free space propagation, and we compare the standard deviation of the long window with our threshold for movement. We then go on to determine the phase, and if it's in an approach, we do the proximity test, and if that passes, we are in a state of surveillance, and then we reset the long window in order to properly detect the whole surveillance phase. Then, when the phase is less than 0, we are in the escape phase. For the experiment and evaluation of the statistical metrics that were derived earlier for the drone detection system, the authors utilized the following hardware and setup. A Raspberry Pi Model A with a USB Wi-Fi adapter was used as the receiver. It was set up in monitor mode to monitor Wi-Fi traffic and is running dump cap to capture and save data of the Wi-Fi traffic. The Raspberry Pi was installed in a window. The original intent was to have the receiver switch channels periodically to cover the entire band. However, during actual experiments, the received packet rate was found to be too low for that. The authors note that multiple Raspberry Pis could be run in parallel to look at different channels and solve this. The preliminary experiments were run with an X8 Plus drone and equipped with a Raspberry Pi running the iPerf2 program and communicating with a laptop that simulated a live video stream. This was so the drone could be run in a more populated area to test the author's hypotheses on the signal properties of a flying drone. They performed 2 short approaches to a window with a receiver in it and found their assumptions about the standard deviations for the long and short windows to hold true. The authors also tested a moving non-drone transmitter, so it wasn't in free space, both indoors and outdoors, and they noted that they got as close as 10 meters to the receiver. And as you can see, since the standard deviation of the small window here in red in both cases breached the threshold, their detection system would not falsely identify these types of transmitters as a drone and cause a false alarm. For the main drone experiments, 2 drone models were used. The DJI Phantom 3 Standard, which was used for movement, attack phase, and proximity, and the Parrot Bebop, which was used for free space propagation. Testing was performed on an old farmhouse surrounded by open land. The noise threshold was determined using the Wi-Fi access point in the house. The top speed of the drones throughout all the tests did not exceed 7 meters per second, and the GPS of the Phantom was used to record flight runs. Here we see the approach patterns for the different tests in the experiment. Most of the statistical metrics were derived from a straight approach. These others are tested to just see how well the system works. They're pretty self-explanatory, except for maybe the no line of sight approach, where we start from outside the field of view of the receiver and then cut in at the last minute before going right to the surveillance distance. Derivation of the statistical analysis was based on the direct approach to the window. However, this also applies to the zigzag and back and forth approaches, as they all have constant line of sight during the approach. It is the no line of sight approach that is different and actually gives the detection system less time to detect an attack prior to surveillance occurring. Here we see the system parameters that were used for the line of sight experiments, and they were derived from the statistical tests that we came up with. Surveillance distance of 1 meter, launch distance of 50 meters, short window of 0.1 second corresponding to our maximum velocity of 10 meters per second. We have our 4 different long windows based on these minimal velocities. We have our noise threshold over here that was calculated from the standard deviation of the noise. And we have our proximity threshold of 10 derived from our surveillance distance. Here for the direct approach, we see with our long windows, we're looking at movement and the attack phase. For the movement, we see that here we have a small increase during takeoff. However, it doesn't actually breach our threshold except for the 5-second window. We then see at stage 2 here, the drone is accelerating to the window. And actually, detection happened quicker than was predicted from our model, mostly due to the takeoff and acceleration instead of a fixed velocity, increasing the actual measured standard deviation. Here at 4, there's a speed decrease here as the operator tried to get better control of the drone as it got closer to the house, so that accounts for that peak there. At 5, this is actually when the surveillance occurs, and you can see for the most part it is below the threshold, and especially over here at this point, after the rolling window catches up to the current data, we're below the threshold. The authors do state how difficult it was to keep the drones still as when they were so close to the window. Then we have our escape phase here and the landing. Now looking at the movement over here, the 10-second and 15-second windows stay positive above this for the entire approach, whereas the 5-second over here you can see dips below multiple times as it's much quicker to respond to the drone slowing down. The 15-second window does breach the proximity threshold early before the drone actually reaches the detection. However, it was not the smallest standard deviation that was above the long window threshold, so there was no early alarm that's produced. It is actually the 10-second window that accurately detects proximity to the window. And then here we can clearly see our escape phase. Here we can see the free space propagation test for the direct approach. We have here our calculated standard deviation threshold. And as you can see, for the short time window, we stay under that for most of the approach until we get to the surveillance distance. It was at this point that it became hard to control the drone due to it being so close to the window. Even with these breaches above this threshold, which would invalidate this transmitter as being a drone, the authors argue that by the time that happens, it can be confidently stated that this transmitter is in fact a drone. During the zigzag approach, two different parameters outside of the determined system parameters were considered in determining the size of the long window. They looked at the actual maximum velocity that was reached during the zigzag approach and the effective velocity throughout the whole approach, and gave these two different window sizes of 6.15 seconds and a much longer 30.225 seconds. For the zigzag approach, we have four different stages marked here. We have the takeoff, where we can see our slight increase over here in the standard deviation. We have our surveillance going on over here, escape and landing. So here we can see that the longer window is much better at depicting the overall approach, surveillance, and takeoff of the drone. However, it is late in detecting that the drone has reached the surveillance distance within this area here. But it does stay above that threshold as expected. Compared to the system parameters, it would seem that the 10-second window here is a best fit, as there's quick detection of the surveillance phase, and we stay below the threshold until we begin our approach. The back and forth approach was approached very similarly as the zigzag approach and gave us two different long window sizes that were used to compare against the system parameters. Similar to the zigzag pattern, the back and forth approach showed similar signs. The smaller time window here showed the actual very erratic behavior of the drone going back and forth, whereas the long time window was more descriptive in general of the overall approach of the drone. Similarly, for the attack phase, the smaller window is very erratic and tends to oscillate between approach and escape throughout the whole time, whereas, as before, the longer window better just shows the approach overall. You can see the takeoff, and you can see the approach where it breaches that proximity threshold and then goes down and begins its surveillance before retreating and then landing. As we can see here, the detection ranges for the line of sight experiments were much farther than the initial predicted 24 meters. So this indicates that the system was better at detecting drones trying to conduct a privacy invasion attack than was originally predicted by the model. For the no line of sight approach, the drone started 28 meters away on the other side of the house and flew up over the roof before dropping into the line of sight and proceeding closer to the surveillance distance. We can see here that between 3 and 4 that the standard deviation increased while the drone was flying over the roof. Then there was one other peak that occurred over here. Now this was as the drone was dropping into line of sight of the receiver, and then there were other peaks over here just as the drone got closer to conduct surveillance. For the no line of sight approach and the free space propagation test, looking at the small term window, the standard deviation of that was very low, despite the lack of a line of sight to the receiver. And the authors believed that the roof, as it was flying over the roof was only attenuating the signal and was not actually causing any of the multipath effects. So the results of the experiments, the detection actually occurred much sooner than predicted. This is attributed to the very conservative model that was used to originally create this system, and the real-world variations such as operator inaccuracy as well as an actual acceleration versus a fixed speed that caused much larger variations in the signal strength. Communication was established prior to takeoff, which was surprising, which resulted in a spike in the standard deviation above the threshold. This allows for an earlier warning of potential incoming privacy attacks to be implemented in the future. The authors also discovered how crucial the live stream video feed is for the operator to conduct a successful privacy attack. They figure it would be almost impossible to do so without one. The authors did mention a potential countermeasure by the adversary to fly the drone close to the ground for most of the approach, which would fail the free space propagation test. However, they assert that at some point the adversary would most likely have to gain altitude to get access to the property, which would render the drone detectable again. In conclusion, for all of the tests that were performed, the drones were detected early in all of the attacks. For each test, an alarm was successfully raised when the drone got within surveillance distance, and they were also able to detect the drones that were approaching with a line of sight and also without line of sight. For future work, the authors discuss studying how the system would behave in an urban environment with more multipath variations. They also bring up using a similar measurement system using the signal strength, but using a wireless device, specifically an Android phone, to create the detection system. They liked that it wouldn't require any specific extra hardware. However, they noted that they would need to study the effects of a dynamic device operating as the receiver.